Hello, I'm Dr. Rachel Howe from the University of Birmingham in the UK, and I'd like to tell you a bit about some of my research interests. As you probably know, we can use helioseismology, study of sound waves inside the sun, to probe below the surface of the sun and build up a picture of its internal structure and dynamics. But that picture isn't static, and that's why it's been interesting to keep studying it over more than 3 solar cycles. Even though the acoustic waves used in helioseismology penetrate deep inside the sun, they're still most affected by the outer layers, the top few percent by radius. And that's where we believe most of the solar cycle effect on the mode parameters come from. The frequencies of the modes are affected by changing levels of magnetic activity. You see some examples in these plots. And the relationship holds over a wide range of temporal scales. We can track it in low degree modes going back more than 40 years and up to the present day. And we can see the signature of individual active regions moving across the disk in the mode parameters from local helioseismology too. But no 2 cycles are exactly alike. And there are hints in the data that the sensitivity of the mode frequencies to activity may itself vary a bit from one cycle to another, which tells us something about how the activity varies with depth in those outer layers, as modes of different frequency are trapped at different depths below the surface and might have different reactions if the thickness of the layer in which the activity is taking place changes. The line width of the modes and their amplitude are also affected. With the amplitude going down, the line width going up, which means that the lifetime is shorter with more activity. And this also holds true for global mode, for local modes. And we can see here the ring diagram frequencies mapped for a Carrington rotation, and frequency, amplitude and line width changes, and at higher frequencies, some of those trends actually reverse. And what's more, even the solar new max, the frequency where the envelope of the oscillation spectrum has its peak, varies a bit with the activity level, which you can see there. Now, helioseismology also lets us see the interior motions of the sun, including the rotation profile, which you see illustrated here, with its well-known features of faster rotation towards the equator and slower rotation towards the poles. But with seismology, you can see that that pattern extends deeper inside the sun. And we have a pretty clear picture by now. They have the radiative interior where the rotation is pretty much a solid body. The shear layer at the tachocline, at the base of the convection zone, which is quite narrow. And then in the body of the convection zone, you have rotation, which isn't quite radial and certainly isn't on cylinders, but somewhere in between. And finally, the outermost thing, there's a near surface shear layer, which explains why if you use different magnetic features to trace the rotation rate, you might get different answers because of how deep they get. The rotation picture isn't static either, and the small changes in the rotation during the cycle make up a pattern known as the torsional oscillation, which is closely associated with the magnetic butterfly diagram, where the active latitudes migrate towards the equator over the cycle. Now, this plot shows the pattern close to the surface after taking out a mean rotation value at each latitude. And you can see these bands of faster and slower rotation coming down towards the equator with each solar cycle. And these belts of faster flow are not just a surface phenomenon, but penetrate through most of the convection zone, as you can see in this movie. And one interesting thing about the torsional oscillation is that the belts of faster rotation appear earlier and at higher latitudes than the active regions do. So we can use them to get an idea of when the next cycle might start. And the historic record, represented here by surface Doppler observations from Mount Wilson, suggests that the activity starts to become widespread around the time that the faster rotating band gets down to about 20 or 25 degree latitude. As represented by these blue lines. So the vertical blue lines show where the cycle is starting, and the horizontal lines are drawn at 35 and 20 degrees. And so you can see where those lines intersect the red, yellow bands. Again, if you look closely, you can see that no two cycles of the pattern are exactly alike, particularly at high latitudes. We can see that the high latitude rotation was slower and the forward moving branch of the torsion oscillation was weaker in cycle 24 in the bottom plot, and cycle 23 in the top. The two cycles look a bit more similar if we subtract a separate mean for each one, which suggests that the underlying rotation profile has changed. But they're still not quite the same, particularly at the high latitudes at the beginning of cycle 25, which you see on the right-hand side of the bottom plot. And finally, plot the residual rotation rate at different latitudes near the surface. And in the bottom plot, you can see that the rotation at 60 degrees, so it peaks quite sharply in cycle 23. Cycle 24, it didn't vary very much at all. And then at the end of cycle 24, it dipped very sharply, but it's now recovering. And, you know, one can't help wondering whether this means that cycle 25 is not going to look quite as similar to cycle 24 as the predictions suggest. So that's what I wanted to tell you about, and thank you for your attention.